how did you get on with assignment 5? Mastery of quantifiers is the one last ability you need to be able to cope with definitions of mathematical concepts and with mathematical reasoning. I'm going to begin by looking at the way negation affects quantifiers. But before I start, let's see how you're progressing by way of a quiz.
Okay, let's see what we have. Is it the case that for every real number x, x plus 1 is greater than or equal to x? Yes, it is. Is it true there is a real number x such that x squared plus 1 equals 3? Well, that would mean x squared equals 2. So we're really saying, is it true that there exists a number x whose square is 2? Well, if we were talking about the rational numbers, the answer would be no, because the square root of 2 is irrational. But for the real numbers, it's true. What about this one? Well, for very large negative x, x cubed is an extremely large negative number which will dominate all of these numbers. So for large negative x, this expression, this cubic expression, is negative. So it's not the case that it's always positive. So that one's false. What about this one? Is it true that for all x there is a y? X cubed plus y cubed equals 0. That would mean y cubed is equal to minus x cubed. The answer is yes. Given any x, just let y be negative x. When you cube a number, you cube a positive number, it's positive. You cube a negative number, it's negative. So by taking y equals negative x in all cases, you'll get 0. So this one's true. What about this one? Is there an x such that whatever y you add to it, you get 0? The answer is no. If the quantifiers were the other way around, the answer would be yes. For every y, there is an x such that x plus y equals 0. Namely, you let x be negative y. But it's not the case there is one x that works for all y. So that one's false. What about this one? Well, is it the case that for all x there is a y such that if x is non-negative, then y squared equals x? Well, let's look. Supposing we took an x. If x was negative, then game over, because this conditional would be true. It would have a false antecedent. If that x was non-negative, then there is a y whose square is x, namely the square root of x. So whatever x we take, there's always going to be a y that satisfies this. It's true. You might have to think about this one a little bit, because there are two cases involved. Given an x, you can find a y that makes this thing true. If the x you're given is negative, any y will make that true. Because if the x is negative, the antecedent is false. But if the x you're given satisfies this condition, if the x you're given is non-negative, then the y you pick is the square root of x. You see what's going on? If you're given a negative x, there is no y that satisfies y squared equals negative x, not in the real numbers. But that eliminates that case. So this one's quite subtle. I suggest you think about this one. It's the kind of thing that you encounter quite a lot in mathematics. Okay? Well, how did you do?
Okay, let's move on. In mathematics and in everyday life, you often find yourself having to negate a statement involving quantifiers. Yeah, of course, you can do it simply by putting a negation symbol in front. But that's not enough. At least often it's not enough. You need to produce a positive assertion, not a negative one. The examples I'll give should make it clear what I mean by positive here. But roughly speaking, a positive statement is one that says what is rather than what is not. In practice, a positive statement is one that contains no negation symbol, or else one in which any negation symbols are as far inside the statement as is possible, without the resulting expression being unduly cumbersome.
Let's look at our first example of negating a quantified statement. Let A of x be some property of x. For example, x is a real root of the equation x squared plus 2x plus 1 equals 0. I'll show that not for all x A of x is equivalent to there exists x such that not A of x. For example, it's not the case that all motorists run red lights is equivalent to there is a motorist who does not run red lights. Well, in this case, it's pretty obvious that these two are equivalent. The proof that I'm going to give in the general case is actually the same reasoning you automatically do when you look at the specific case. If it seems hard to follow, the issue is purely one of the abstraction. I'm proving an equivalence, so I'm going to prove an implication from left to right and then from right to left. So we begin with the left to right case. I'm going to assume not for all x A of x. Well, if it's not the case that for all x A of x, then at least one x must fail to satisfy A of x. So, for at least one x, not A of x is true. In symbols, there exists an x such that not A of x is true. Well, that's the left to right implication. I assumed not for all x A of x, and I concluded there exists an x not A of x. Now we want to do the other implication. So, assume exists x not A of x. Well, in this case, there's an x for which A of x is false. That's just expressing this in everyday English. Well, if there's an x for which A of x is false, then A of x cannot be true for all x. In other words, for all x, A of x must be false. Expressing that in symbols, it's not the case that for all x, A of x. And now I've proved the second implication from exists x not A of x to not for all x A of x. Assume exists x not A of x, conclude not for all x A of x. If you found this reasoning hard to follow, it's purely because of the abstraction. The logic is exactly the same as in the example. Almost certainly you had no difficulty with this example, and that's because you're familiar with this situation. The human brain is very good at doing logical reasoning about familiar situations. When we turn those situations into abstract versions, the brain finds it difficult, at least at first. And in fact, one of the things about becoming a mathematician is learning to take familiar everyday reasoning that we don't even think about, we just do it automatically, and reproduce it in an abstract situation. And it's the abstraction that's causing you difficulty. You can follow the logic, but you find it difficult to follow it in an abstract situation. And that's just because of the way the human brain works. Okay, why don't you try this one? Show that not there exists an x A of x is equivalent to for all x not A of x. And before you start, you might want to look at an everyday example. This is coming up as an example in the assignment for this lecture, but you might want to try it now while this example is fresh in your mind. Okay, good luck on that one. With that one under our belt, now we can go back and look at that earlier example of the negation of all domestic cars are badly made. Let C be the set of all cars. D of x means that x is domestic, and M of x means that x is badly made. With this notation, the sentence becomes, for all x in C, D of x implies M of x. For all cars, if the car is domestic, then it's badly made. Well, we've already seen what happens when you negate a universal quantifier. The negation becomes, there exists an x in C such that dx does not imply M of x. And here I've actually abbreviated the following. Not the case dx implies M of x. Well, it's not much of an abbreviation, but instead of writing not dx implies M of x, I've used this simpler notation, dx does not imply M of x. Okay. But in any case, looking at our previous example, the one that I illustrated with the motorist, when you take for all x something and you negate it, you get there exists x with the negation of the thing inside. Just compare what's going on here with the previous example. One comment, why am I not saying exists x not in C? Beginning students often do this kind of thing. And the reason they do it is they are trying to go through a formula symbolically and negate things. And that's not the way to go about these things. You've got to think about what the symbols mean. In this case, it's talking about x's which are in C. The only x's we're interested in are x's which are in C. In other words, the only objects we're interested in are cars. But if the only objects we're interested in are cars, the negation will only be talking about cars. So the in C part simply tells us which kinds of objects we're dealing with, and we don't negate that. Okay, now let's look at this part. We know that dx does not imply M of x is equivalent to d of x and not M of x. In fact, this was the key part of our reasoning to figure out the truth table for the conditional. D of x does not imply M of x if d of x can hold and nevertheless M of x can fail. So we looked at this when we did truth tables. So the negation of the original sentence which is this, is equivalent to there exists x in C this part is the same as this part, d of x and not M of x. Well, what does this mean in everyday language? It means there is a car which is domestic and is not badly made. And that's it. So if you found it difficult to figure out the negation of this sentence when we first looked at this example, now, because we've got this notation and this little method for dealing with these negations, you should be able to follow it through fairly straightforwardly. Moreover, the previous time when we looked at this, even if you got the answer, you might not have been totally confident that you got the answer right. This kind of reasoning makes it clear that this is the right answer. And that's the whole point of introducing this formal notation and this logically precise reasoning. We're no longer left not certain if we've got the exact, best, correct, logically correct negation. The mathematics leads us to the answer. And that is the correct answer. Okay, let's do another example. Let's look at the claim, all prime numbers are odd. Now we all know that this is false. And we know it's false because we know that 2 is a prime number which is not odd. But let me tease apart the logic that underlies that conclusion. Because in more complicated situations where we're not familiar with the domain or with the result, all we'll have to use is the logic itself. So I want to make heavy weather of this in order to understand the kind of reasoning that we'd use in situations where we don't know the answer. Okay. So I'm going to let P of x mean x is prime, and I'm going to let O of x mean that x is odd. So the sentence can be written symbolically as for all x, if x is a prime, then x is odd. When I negate this, I get exists x, not px. Here's O of x. Or another way of writing it, there is an x such that P of x and not O of x. The negation of not for all x, P of x implies O of x is there exists an x such that P of x and not O of x. In words, i.e., there is a prime that is not odd. So in order to prove that this is false, which is the same as proving that the negation is true, the logic says find a prime that is not odd. And we can. 2 is a prime that's not odd. So if I want to prove conclusively that this statement is false, which is the same as proving that its negation is true, what I need to do is demonstrate that there is a prime that's not odd. And in this case, that's immediate. We just pull 2 out of the hat, observe that 2 is prime and it's not odd, therefore the negation is true, the original statement is false. Well, in that simple example, that was making much ado about nothing. But in more complicated situations, going through the underlying logic is often the only way forward. By now you should have noticed the pattern of behaviour that's happening with these symbolic negations. When we negate, a for all becomes exists, and the for all sort of jumps inside, and when it jumps inside we can manipulate it and get the result into a positive form, where the negation is at the most innermost point. You can actually turn these into formal symbol manipulation rules, and which means you can implement them on computer systems, and there are computer systems that do this kind of reasoning for you. I'm recommending very strongly that you don't do that, because what we're trying to get at is mathematical reasoning, and moving symbols around, doing symbolic manipulation is not mathematical reasoning. It's connected with mathematical reasoning, it supports mathematical reasoning, we can use it in mathematical reasoning, but the real essence of what we're trying to do is to understand what the statements mean, understand what the symbols represent, and reason with the concepts. It's reasoning with concepts that mathematical thinking is all about, not symbolic manipulation. Okay, we showed that this was false by finding a counterexample. In this case, the counterexample was 2. Supposing I modify it as follows. All prime numbers bigger than 2 are odd. In symbols, for all x bigger than 2, if x is a prime, then x is odd. Okay? Now I'm going to give you a quiz. What is the negation of this statement? Is it 1, there exists an x less than or equal to 2, such that p of x and not o of x? Or is it 2, there exists an x greater than 2, such that p of x and not o of x? Okay? Which one of those two do you think it is? Well, the correct answer is 2. It says there exists a number bigger than 2, which is prime, it is not odd. That's the negation of that statement. Why isn't it number 1? Well, because the original statement is about numbers bigger than 2. So the negation must be about numbers bigger than 2. We don't simply negate every symbol in sight and say, well, in terms of the ordering on the real line, if we negate something being bigger than 2, then it means it's less than or equal to 2. That's a symbolic negation, that's a sort of a detailed, localized negation about the ordering on the real line, but the sentence as a whole means something about all numbers bigger than 2. So its negation means something about all numbers bigger than 2. Okay? Well, let's move on. Let x denote a person. Let P of x mean x plays for sports team T. And let H of x mean x is healthy. And let me look at the statement, there is an x such that P of x and not H of x. What does that mean in everyday English? There is an unhealthy player on team T. Now let me negate that. I'm going to find the negation by symbolic manipulation. Now this, remember, is the method that I'm suggesting that we don't use. I'm doing it that way in order to illustrate the mathematics and the underlying logic. If we negate this, we know that when we negate an exists, it turns into a for all. And then the negation moves inside, if you like. And then when we move that negation inside, we get not P of x or H of x. So the negation moves inside. We get P of x becomes not P of x. When we negate a conjunction, we get a disjunction. And when we double negate something, we get the original thing back. Remember, this is not the way I'm recommending you do it. I'm doing this as an illustration of the underlying logic. Well, this thing looks familiar. Remember when we looked at the conditional? P conditional Q means the same as not P or Q. They had the same truth table. So this guy can be rewritten as P of x, here's H of x. In English, all players on team T are healthy. Well, is that the negation of that? There is an unhealthy player on team T. Well, if it's not the case that there's an unhealthy player on team T, then all the players on team T must be healthy. Which is definitely the case. That is definitely the negation of that. And again, let me stress, this is not the way you should do this kind of thing. I'm using this to illustrate how negation behaves with quantification. Next point. Suppose I write down a sentence like the following. For all x, if x is greater than 0, then there is a y such that xy equals 1. Is that true or is it false? Well, there's no way of knowing. It depends what the x denotes. If x denotes a motorist or an automobile or a healthy team player, it's completely nonsensical. If x denotes a natural number, it makes sense, but it's false. If x denotes a rational number, it makes sense and it's true. But the point I want to make is that a quantifier only tells you something if you know what the variable denotes. Associated with any quantifier, we have what's called a domain of quantification, which tells us what does the x denote. If the domain of quantification is obvious, if we've set it in advance or the context makes it clear what it is, then we can use statements like that. If there's any danger of misunderstanding, if there's any potential ambiguity, we can make the quantifier more explicit by stating the domain of quantification. To make this more explicit, I could write it as, for all x in the set of rational numbers, if x is positive, then there is a y, so it said xy equals 1. And now I've got a true statement that's unambiguous. It tells us that for every positive rational, well, wait a minute. I haven't actually been explicit as to what the y is, have I? Now, arguably, having made it clear that the x denotes a rational, it's reasonable to assume that the y denotes a rational. But if I want to, I could be even more explicit and say for all x in Q, if x is greater than 0, then there is a y in Q such that xy equals 1. I think most mathematicians would agree that if you're explicit about the quantifier at the beginning of a statement, then absent any indication to the contrary, the other quantifiers denote the same thing. But if there's any possibility of misunderstanding or if there's any potential ambiguity, it's better to be explicit everywhere as to what the quantifiers denote. Something else you need to be aware of with regards to quantification is that mathematicians sometimes omit the quantifier. We write things like, if x is greater than or equal to 0, then square root of x is greater than or equal to 0. If you see an expression like this, what that means is the following. For all x, perhaps in R, or perhaps in something else, for all x in R, x greater than or equal to 0 implies square root of x greater than or equal to 0. Or something like that, depending on what the x denotes. I've assumed from the context, and this is a reasonable assumption, I've assumed that the variable is meant to range over the real numbers. Even though there's no explicit quantifier here, this would be read as meaning something like that. This is what's known as implicit quantification. The mathematician is simply leaving out of the formal expression any explicit mention of the quantifier. It's left implicit in the way this is written. Now, this is a fairly advanced point. I'm certainly not recommending you do this, but the professionals do this all the time, so you need to be aware of it in case you come across it in something that you read. But please avoid doing this. I realize by saying this that I'm saying do as I say, not as I do, because like all professional mathematicians, I do write things this way all the time. But while you're still learning about these ideas, it's best to avoid doing it, because if you don't use this in the right kind of context, all kind of difficulties can arise. And having given you one caution, let me give you another one. This is about combining quantifiers with conjunction and disjunction. Let me just do this by way of an example. Let n, the set of natural numbers, be the domain of quantification. Let e of x mean x is even, and let o of x mean x is odd. look at the formulas for all x, e of x or o of x, and for all x, e of x, or for all x, o of x. I guess I don't need that last bracket, right? Okay, for all x, e of x or o of x, and for all x, e of x, or for all x, o of x. Notice that the first one is true. It says for every natural number, it's either even or it's odd. What does the second one say? It says every natural number is even or every natural number is odd. Well, that's false. Well, the point I'm trying to make here is you can't just take a for all and take it inside a bracketed expression. If you do that, you're likely to end up turning a true statement into a false statement or vice versa. Similarly, if I take there exists x, e of x and o of x, we'll do it with an and this time, and I'll take exists an x, e of x, and exists an x, o of x. Again, I've put that extra bracket in there. Can't stop myself doing that. What have I got? This says there is an x which is both even and odd, which is false. What does this one say? There is an x that's even and there is an x that's odd. That's true. So the same thing happens with exists and conjunctions, say. You can take an existence statement like this, and in this case it's false, but if you pair them up in this way, it's true. In other words, be very careful when you're reasoning with quantifiers, conjunctions and disjunctions. You can't simply take things inside the way you sometimes do in arithmetic. If you think about what these things mean, you're not likely to run into that difficulty. But if you start treating these as symbolic expressions to manipulate, then things could go badly wrong. Okay, enough of these warnings. Let's move on to something else. And this is the last point I want to make about quantifiers. Suppose we're having a discussion about, let's say the real numbers. So if we have variables x, y and z, they're assumed to denote real numbers. The domain of quantification will be the set of real numbers. And in the course of the discussion about the real numbers, we want to talk about rational numbers, or particular rational numbers. We might want to mention that there's a rational number x. Well, there's one way we can do that. We can talk about the rational number in this context. We can say there is an x in Q, or we can say for all y in Q. Or if I want then to talk about a natural number, I can say for all n in the set of natural numbers. So by introducing explicit domains of quantification in this way, in the course of discussing real numbers, I can restrict attention to particular rationals or natural numbers or whatever. And so in the course of an argument, I can actually use multiple domains of quantification. Well, in examples like this, where we're talking about different sets of numbers, this is fine. But in other situations, it really doesn't make sense to introduce multiple domains of quantification. For example, suppose I'm going to be talking about, let's say animals. So suppose the domain of quantification is the set of animals. And then I might want to say something like, every leopard has spots. Well, how would I do that? Well, I suppose I could say, for all x in the set of leopards, x has spots. But in the next sentence, I might want to talk about tigers, and then giraffes, and then who knows what. And very soon, I could have a whole range of different domains of quantification floating around. And that's not very clean, it's not very nice, and it's certainly not very sensible. Because the discussion isn't really about leopards or tigers or giraffes or whatever. It's about animals. And if the discussion's about animals, then the set of animals should be the domain of quantification. So instead of writing something like that, what I should write is for all animals, if that animal is a leopard, then it has spots. That allows me to say something like, there is an animal which is a horse and has spots. There's a spotted horse. Or I could say, for all x, if x is a tiger, then x doesn't have spots. The point is, if I'm talking about animals, then when I refer to specific animals, I'm not changing the domain of quantification. I'm still talking about animals. I'm just describing properties of particular kinds of animals. The discussion is still about animals, so the domain of quantification should be animals. It's different here because the domain of quantification arguably is the set of real numbers or the set of all numbers. And then, because we have these standard subsets, it's okay to introduce things like this. You don't have to. You could actually use something analogous to this. But in this kind of situation, yes, if you're talking just about real numbers, then you really don't want to be introducing particular subdomains. You should use the analogue of these kinds of expressions and talk about if it's a rational than this, if it's a natural number than this. But if this is really a discussion about all numbers, not just the real numbers, then these are just particular categories of real numbers and natural numbers and so forth. And you can have subdomains. You can have different domains of quantification. This isn't an issue of right or wrong. It's an issue of whether it's sensible and helpful to work in a certain way. And using separate subdomains of quantification is fine if they are natural domains and it makes sense to talk about it that way. But the idea of a domain of quantification is that that tells us what it is we're talking about. If we're talking about animals, then don't introduce different domains of quantification that are not animals. Even if they're subdomains, it gets complicated. Okay, that's enough about quantifiers for now. I suggest you go away and see how you get on with assignment number 6.